Good morning, students. Only 63 people have to join here. morning, students. So now in today's class, we have to discuss with the timing constraints in sequential patterns. So we have the remaining two topics only in this unit, subgraph patterns, and second one is the infrequent patterns. So totally patterns are you have to represent it with the three ways. One is the sequential patterns, and second one is the subgraph patterns, and third one is the infrequent patterns. By these three ways, you have to represent the data. So in sequential patterns, how we can represent it with the timing constraint. Based on timing constraints, you have to represent the patterns of a sequential pattern formulation where the timing constraints are imposed on the events and elements of your pattern. To motivate the need for the timing constraints, following sequence courses like, for example, a student will have to join in a particular course like statistics, database management system, and data mining. So a student, first student will have to join these three courses, and second student they want to join the courses like database management system, DBMS, and statistics and data mining. In the first student joined in a sequence like statistics, DBMS, and data mining. But the second student pattern is DBMS, statistics, data mining. So subjects are same, but the order of the sequence is different. Okay. For example, this sequential pattern I want to define as a first they want to learn these two subjects. First one is the statistics, and the second one is the database management system, or simply call it as DBMS. In this sequential pattern, we want to learn statistics and DBMS in parallelly, and then they are to learn the data mining. So first, they must be know these two subjects regarding to the statistics and DBMS. So here, which means that the students who are enrolled the data mining class, he must previously taken a course in statistics and DBMS. So the pattern is supported by the both students, even though they do not take the statistics and DBMS at the same time. So here a student can took the statistics course 10 years earlier should not be considered as a supporting the pattern course, supporting the pattern, because the time gap is occurs too long. Because the formulation is presented in previous section does not incorporate these timing constraints. So first of all, parallelly they want to complete both the courses. So statistics and DBMS for the student A and student B. Once they completed these two courses, then they want to join in data mining. So like this way, we have to represent the timing constraints. So here we have to represent the two types of constraints. One is the gap related, and second one is the span related. So maximum span constraint we have to represent it, and as well as minimum gap constraint we have to represent it, as maximum gap also we have to constraint we have to represent it. First one related to the span. The maximum span of the constraint specifies the maximum allowed time difference between the latest and the earliest occurrences of events in the entire sequence. For example, you have to see the data. For example, suppose the following data sequence contains events that occurred at consecutive timestamps. At consecutive timestamps 1, 2, 3, assuming the maximum span is 2, 3. So here the consecutive timestamps are 1, 2, 3. That is the maximum into 3. So here the maximum spanning is 3. The following table the maximum so here we have to see the maximum span constraint affects supporting count step of the sequential pattern discovery algorithms. So here the maximum span is detected to a pattern in a data sequence. The longer maximum span is also be captured by the different various patterns because it increases the chances of unrelated events to be temporarily related. So here the maximum span of a particular thing here we have to represent it is 1, 3, 3, 4, 4, 5, 6, 7. That is the data sequence I want to reading 8. So the sequential pattern is 3 and 4. So it is sequential S. So after 3, 4, you are getting the 4. So it is the sequential pattern. And the second one, 3, 6. We want to consider here the pattern is data science 1, 3, 3, 4, 4, 4, 5, 6, 7, 8. So I want to represent it here. For example, here you have to consider the maximum gap and window size, minimum gap. So we have to discussing here. Data sequence is D 2, 4, 3, 5, 6, 4, 7, 4, 5, 8. That is the data sequence. And the sequential pattern is 3, 4, 5. So 3, 4, 5. So D contains in S a pattern. So 3, 4, 3, 4, 5. So here the starting with the item is 3, and second data sequence in the data sequence we have to represent the 4, 5. So 3, 4, 5 is there in the sequential pattern. So D contains S. D contains S. That is the second case. 1, 2, 3, 4, 5. That is the pattern. That is the data sequence. In the sequential pattern, 1, 2, 3, 4. So one is not a list of items. So it is a list of item set. Here we can represent the 1, 2 is the item set. One item set. 3, 4 is another item set. So that is not a sequential pattern in the data science of D. So D contains S is no. That's the reason you can say that no. And a similar way, 1, 2, 2, 3, 3, 4, 4, 5, that we have to represent it. One, two, two, three, three, four, four, 5. That is the data sequence. See here, 1, 2, 2, 3, 3, 4, 4, 5. But the sequential pattern is 1, 2, 3, 4. See here, in the data science, you have the 1, 2, 1, 2 item set are there, and as well as 3, 4 items set are there. Both are there in the data science. So this sequential pattern is there in the data science, data sequence. So it is a D contains S is S. That is the way you can say that. But in the second one, only the individual items are there. That is the 1, 2, 3, 4, 5. But that is not an item data sets. That is the 1, 2, 3, 4. D contains S. No, that is the way we can say that it is a no. This is the regarding to the maximum span. For example, to support counts or some of the patterns may be overestimated. to avoid this problem, the algorithm must be modified to ignore cases where the interval between the first and the last occurrences of events in a given patterns is greater than the maximum span. So here you have the four terms you have to represent. One is the minimum gap, second gap, that is maximum gap, maximum span, and the window size. See here how we can represent it in following here. This is the pattern you have to consider. Data signs A, B, C, D, and D. AB is the one data item set, and C and D is the another data set item set. So totally the items are A, B, C, D. So now we have to consider maximum gap. How we can say that? That is the XG. That is the XG. What is the maximum gap? We have to represent it here. That is the 2. Is less than or equal to XG. That is the maximum gap. A, B, that is the AB is the one item set, and C. So totally maximum gap is 2 here. That is the max gap is the 2. And the second one is the NG, that is the minimum gap. So C in between the CD and E don't have the only one gap only. So this is the one item set. This is the AB is the item set, and C is the individual item. So totally the gap is you have to represent it as in between the A and C you have the 2. So that is the way you can say that maximum gap is 2. And the minimum gap is C and D. We have the less than greater than equal to NG, that is the minimum gap. So here the minimum gap is 0. And the next one is the window size. Window size is 1. Simply you can say that WS is, we can represent it here. That is always greater than window size. Less than or equal to WS, that is the window size. That is the maximum span is simply you can say that 5. It is the A, B, C, D, E. That is the maximum span is 5. That is the way we can say that. This is the simple, easily you can understand the timing constraints regarding to the maximum gap and the minimum gap, window size, and maximum span. So this is the note down. Easily you can understand the timing constraints in the sequential patterns. Take a snap. This is very important. Easily you can understand compared to the textbook. This is the simple timing constraints, or very important timing constraints on sequential patterns. Minimum gap and maximum gap, window size, and maximum span. So timing constraints is also specified that restrict the time difference between the two consecutive elements of this sequence. That is simply you can say that timing constraints on minimum gap and maximum gap. The maximum time difference in 1 week generally we have to call maximum gap. Then the events of one element must occur within the week time events occurring in the previous element. If the minimum time difference is 0. So that is the minimum gap, maximum gap, window size, and maximum span. Window size constraint, generally we can call it as a window size threshold can be defined to specify the maximum allowed time difference between the latest and earliest occurrences of events if any element of the sequential pattern. A window size of 0 means all events in the same element of the pattern must occur simultaneously. If the window size is 2, we can represent the to determine whether a data sequence supports in a given sequence. Minimum gap is 0 and maximum gap is 3, then the maximum span is infinity. In that cases, we can represent it as window size is 2. So remaining cases, you have to represent it as 1. So here you have to represent it as window size is 1. So what are the alternative counting schemes you have to represent it? modified counting steps you have to use. That is if the given candidate is sequential pattern AC and any data sequences that contain, you can represent what is the time differences to contributing the support count of the candidate patterns. You can represent here. There are several methods available for the counting the support of the candidate case sequence from the database sequences. For example, here we have to consider the problem of counting the support of sequence P and Q. WS equal to 0, minimum gap is equal to 0, minimum gap, maximum gap is 1, and maximum span is 2. So these are the four values you have to know. So now we have to comparing the different counting methods. First one is the COBJ, that is the one occurrence per object. CWin, one occurrence per sliding window. C min win, that is the number of minimal window of occurrences. C dist underscore 0 O, that is the distinct occurrences with the possibility of even timestamp overlap, and C dist. So this is the distinct occurrences with no event timestamp overload allowed, timestamp overlap allowed. So these are the totally five alternative counting schemes you have to use in the timing constraints in sequential patterns. So each one you have to represent the diagram. I will show you. So this is the supporting counting schemes here. See here, this is the counting scheme. COBJ, general support counting schemes. These are the 5 types of counting schemes are there. Here we have so here the 5 schemes are there. Those schemes are, first one is the COBJ, that is simply you can say that one occurrence per object. This method looks for the at least one occurrence of the given sequence in object's timeline. So see here, that is the 1, 2, 3 you have to represent P, Q, Q, Q. So this is the object timeline. P, 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 Q, P, Q, Q, P, Q, P, Q, Q. So this is the object timeline, and a sequence you have to represent it as PQ. Method, which method you have to use? What is the support count that you have to represent it here? So what is the PQ you have to represent? First one is COBJ. Its support count is 1. One occurrence per object. That is simply call it as one occurrence per object. This method looks at least one occurrence. See here, one occurrence per object. This method looks for at least one occurrence per a given sequence in object's timeline. The above this diagram will shows even though a sequence of PQ appears in several times in the object's timeline, but it is counted only once with the P is occurring at T equal to 1. So first one we have to consider PT equal to 1, and Q is occurring at third position. That is, you can say that T is time occurrences at the 1, and the Q is occurred in timing occurrence at the 3. So that is the PQ you have to represent. That is the COBJ, one occurrence per object. అంటే ఇక్కడ మనకి 2 ఈవెంట్స్ ఉన్నాయి. వన్ ఈజ్ ద పి అనే ఈవెంట్, సెకండ్ వన్ ఈజ్ ద క్యూ ఈజ్ ద ఈవెంట్. ఈ 2 ఈవెంట్స్ ఎక్కడైతే ఫస్ట్ టైం అక్కడ అవుతాయో దట్ ఈజ్ ఓన్లీ యూ హ్యావ్ టు కన్సిడర్. అంటే పి అనేది మనకి ఫస్ట్ టైం స్పాన్ 1 లో టైం లైన్ లో 1 లో మనకి అక్కర్ అయింది. క్యూ అనేది థర్డ్ పొజిషన్ లో అక్కడ అయింది. So only these two only we have to consider. Okay, clear? That is the COBJ, one occurrence per object. So you are using this method, supporting method, that is simply can one occurrence per object that is used for, that is the COBJ, that is the method we have to use for the supporting counting methods. And the second one is the CWin. CWin means one occurrence per sliding window. One occurrence per sliding window. So totally here you have to consider in this approach, a sliding window, time window for fixed length, maximum span is moved across the object line, one unit at a time. The support count is incremented each time the sequence is encountered in the sliding window. In this diagram, it shows PQ is observed 6 times using this method. And P అనేది ఎన్ని టైమ్స్ అక్కడ అయింది, Q అనేది ఎన్ని టైమ్స్ అక్కడ అయింది. సో వన్ అకరెన్స్ పర్ స్లైడింగ్. సో ఒకే వెబ్ పేజ్ మీరు 10 టైమ్స్ ఓపెన్ చేస్తారు. సో 10 టైమ్స్ యూ హ్యావ్ టు రిప్రజెంట్ ఇట్ within that slides only. That is the first web page, second web page, third web page. Like this way, continuously we have to represent. Similar way, here also we can represent the one occurrence per sliding windows. Number of sliding windows we have to represent it. Okay, sir, మనం web pages 10 ఓపెన్ చేసాం అనుకోండి, one by one మనం continuous color sliding the display అవుతుంది. Similar way, this is the one. That is the one occurrence per sliding window. See here, P is occurred at the Q point, and P is occurred at the Q point. So 1, 3, 2, 4, and 3, 5, 3, 5, and 4, 6, 4, 6, and as well as 5, 5, 7, and see here totally P is occurred in 6th position, then next position, that is totally 6 occurrences will be occurred in P, and Q is occurred 6 times. That is, you have to represent it as CV, one occurrence per sliding window. So totally in this diagram it shows PQ are observed 6 times using this method. And the next one is the CMin-Win, number of minimal windows of occurrence. Number of minimal windows occurrence. A minimal window of occurrence is the smallest window in which the sequence is occurs giving the timing constraints. In other words, the minimal window is the time interval such that sequence occurs in that time interval, but it does not occur in any of the proper intervals of it. This definition can be considered as a restrictive version of CV, because its effect is to be string and collapse some of the windows that are counted by CWin. For example, sequence PQ are there. In the PQ, 4 minimal window occurrences are there. First pair is after P, you are getting the Q. That is the at the T2 and first pair you have to T equal to the 2 timing constraint at 2 place, and Q equal to at the T3. And the second pair we have to represent it T is 3 and Q is 4. That is the second pair. And next one is the fifth and sixth. Next one is the sixth and seventh. So totally 4 pairs, 4 minimal window occurrences are there who are occurring in C min win. So to the occurrence of event P equal to T equal to 1, event Q at the T equal to 3, not a minimal window occurrence because it contains a smaller window with the T equal to 2, T equal to 2 and T equal to 3, which is need a minimal window of occurrence. మనకి యాక్చువల్గా PQ అని P equal to 1 and Q equal to 3 తీసుకోవచ్చు, కానీ ఇక్కడ మినిమల్ అక్కరెన్స్ తీసుకోవచ్చు, మినిమల్ అక్కరెన్స్ అట్లీస్ట్ 1. సో that's the reason you have to consider at the time constraints as the 2 and 3 only you have to consider as a page. Okay, that is simply called it as number of minimal windows occurrences. And the next one is C dist underscore O, distant occurrences with the possibility of event timestamp overlap. Event timestamp overlap. A distant occurrence of the sequence is defined to be a set of event timestamp pairs such that there has to be at least one new event timestamp pair that is different from the previously counted occurrences. Counting of such distance occurrences results in the distant C dist O underscore O method. If the occurrence time of events P and Q denoted as a tuple T of P comma T of Q, then this method yields to 8 distinct occurrences of each sequence. PQ, that is the times 1 3 and 2 3 2 4 3 4 3 5 5 6 5 7 and 6 7. So total 8 occurrences are getting for the PQ, that is the distinct occurrences with the possibility of event timestamp overlap. So this is the total occurrences. Totally 8 occurrences will be occurred in the C dist underscore O. And the last method is C dist method. Distant method you have to represent it as distant occurrences with the no event timestamp overlap allowed. So here you don't have any overlaps. In previous case, the overlap is occurred, but here you don't have the overlaps. That only you have to consider. So see here, in C dist underscore O, we have the two occurrences of sequence are allowed to have the overlapping events timestamp pairs are there. Overlap between that 1 3 and 2 3. In the C dist method, no overlap is allowed. Okay, clear? Effectively, when and the event timestamp pair is considered for the counting, it is marked as used and never used again. Subsequent counting of same sequence. Example, I want to say here, find 5 distinct pair you have to getting out of 8 non-overlapping occurrences of PQ. Show here the occurrences at times 1 3 2 4 3 5 5 6 and 6 7. This is the not overlapping occurrences, that is a C dist. These occurrences are subsets of the occurrences observed in C dist underscore O. These are the methods you have to use, support counting methods you have to use it here. And you have the only remaining 2 concepts are there in entire syllabus. So that is the subgraph patterns, and the second one is the infrequent patterns. These 2 patterns are remaining. Once you have to see the subgraph patterns, the application of association analysis methods, more complex entities beyond the item sets and sequences. Example, chemical compounds, 3D productions, protein structures, network topologies, pre-structured XML documents. So these are the graph representation entities of various application domains. I want to say that application, what is the application, what is the graphs, and what is the vertices and the edges. I want to say in graph representation, all these things, web mining, computational chemistry, network computing, semantic web, bioinformatics. So these are the different types of applications. In these applications, whereas in the web mining, you can use the graph web browsing patterns you have to use. Whereas in computational chemistry, you are using the graphs like structure of the chemical compounds. And similar when network computing application, you can use the graphs computer networks. Whereas in semantic web in application, you can use the graph collection of XML documents. Whereas you have to consider the bioinformatic application, protein structure. So protein structure you have to represent it here. Thumb related you have to represent the bioinformatics application. So different types of one type of application can use the one type of graph. So how these graph patterns we can use in a association analysis, you can discuss it here. For example, here in the data web binding, you have to consider the application. The graph is web browsing patterns. What are the vertices? Okay, web pages. What are the edges? Hyperlink between the pages. Okay, that is the way you can say that graph representation of entities for the various application domains. Whereas I want to say that one simply you can say that one application like the computational chemistry. In the computational chemistry, you can use the structure of the chemical compounds. So you know the compounds, what are the atoms are there, what are the ions are there, what are the bonding structure in between the atoms and ions that you have to represent. So here in that chemistry, computational chemistry, to how you can graph, you have to represent the structure of the compound, you have to represent the graph. What are the vertices and what are the edges? So vertices are represent the atoms, and what are the edges? You have to represent the bonding between the atoms or ions. Simply you can say that. This is the graph representation of entities for the various application domains. So here you can represent here. That is the regarding to the subgraph patterns. In next class we can discuss it here. Frequent subgraph mining, subgraph patterns, graphs and subgraphs. Frequent subgraph mining, we discuss it here. A priori like method you have to use it here. So in every case, not only in sequential, in subgraph patterns, sequential patterns or subgraph patterns or infrequent patterns, we can use the a priori like methods you have to use. Frequent item sets you have to present it as in a priori algorithm. But over here we can call it as frequent subgraph mining. Frequent subgraph mining. So like methods you have to use it here. So we'll continue in next class. If you have any doubts regarding to this one, again I want to revise this revise the concepts. If we have any doubts regarding to this one, please chat on chat box. Thank you. So everyone must be submit the assignment one today itself. If in case last day who did not who does not submit the assignments, submit now. Thank you.